Faraday's law of electromagnetic induction is the basis of all generators. Um, Basically, what it states that anytime you have magnetic flux, which is changing with respect to time, that is it is an alternating flux or any flux that is changing with respect to time, and if this flux is linked with a coil, then a voltage is going to be induced in this coil, right? So that's what basically that's the basic idea of Faraday's law of electromagnetic induction, and that's the basis of power generation through turbines. So the voltage that is induced in a coil is directly proportional to the rate of change of flux, which is linking the coil. And when you change the proportionality sign into constant, then it's number of turns of the coil n. So E induced is equal to N dphi over dt, and you see a negative sign over here. This negative sign basically is in accordance with Lenz's law, as you can see over here, Lenz's law. And basically what it says is, if you have a coil and you have a flux that is linking with the coil right here, let's say flux is linking with the coil, and the voltage is going to be induced in the coil. Now if you short circuit this coil, since voltage is induced, if you short circuit this coil, then due to this induced voltage, whether it is positive on top or negative on top, irrespective, due to this induced voltage, the current that will run into this short circuit and pass through this coil, it will produce its own flux. Remember, anytime current passes through a coil, it produces its own magnetic field. Now this magnetic field is going to oppose the original magnetic field that was the cause to produce this induced voltage, and that's the reason of this negative sign basically. So basically it states the direction of the induced voltage is such that the coil is short circuited, it will run a current that will produce a flux that will produce a magnetic field that will oppose the original flux. Okay, so many times we are just calculating the magnitude of induced voltage, and we don't worry about the negative sign over here. But negative sign again is that's why the negative sign is there in your book. Actually, if you look in your book, they don't have the negative sign. Actually, they're not even going to the differential equation. They are giving you this equation right here, delta phi over delta t and delta phi over delta t, and they are not discussing negative sign. But again, negative sign is a standard, that's why I'm putting the negative sign in this equation. Delta phi over delta t is the same thing as d phi over dt, except again your book is written at the level of associate level, and they're not going into the differential equation or vector analysis. But since we are at an advanced level and most of you know how to deal with basic differential equation, then of course I'm going to use what is standard for the bachelor's level. So either d phi over dt or delta phi over delta t. Delta phi over delta t means that you are not observing the rate of change at a small level. You are basically observing the rate of change at a larger scale. So if you look at example 2.2, a coil with 10 turns and linked with alternating flux, calculate the magnitude of induced voltage at t is equal to 23 millisecond. So since we are calculating the magnitude of induced voltage, we take the absolute value of that, calculate the derivative of this equation with respect to time, and we go ahead and multiply that by n10 and go ahead and put t is equal to 23 millisecond in the equation, and it is going to be extremely small voltage. And I think that's my number, the number that I took. It just produced a very small voltage, and most of you, if you're using your calculators or something, you're gonna just observe that it's 0. So don't worry about it, because it's picovolt. It's extremely small value. I just used MATLAB and I put it in the engineering format, so it gave me the picovolt over there. But again, this is just because I'm taking a time at which it is almost 0. If you change the time, of course, you can find the value which is non-zero. Another example, to use this equation, delta phi over delta t. Look at this example, you will understand it. It's pretty straightforward. Let's also look at voltage induced in a moving conductor. So if you have a conductor in a magnetic field and you are moving that conductor with some velocity, then according to Faraday's law of electromagnetic induction, of course, the magnetic field is changing through that conductor with respect to time. The voltage has to be induced in that, right? So if you know the velocity with which the conductor is moving, and velocity is a vector, if you know the magnetic flux density, which is also a vector, you can calculate the induced voltage using this equation. This is a basic equation right here. I expect you that you remember these equations. Of course, you'll be taking an exam at home or quizzes at home, so you always have these equations at hand, Faraday's law equation or induced voltage. But these are the very basic equations that as an electrical engineer or a person who is studying the power system, that person needs to know these 2 or 3 equations, which makes the basis of power generation. So induced voltage will be L dot V cross B. L is the length vector of the coil which is moving in the magnetic field with the velocity B, right? So the natural question is, how do you calculate length as a vector? So the way we calculate length as a vector is, of course, length has a magnitude, the coil that is experiencing the magnetic flux, the magnitude or length of that coil, let's say 10 meter for example. And what will be the direction of that 10 meter long coil? So the direction of that 10 meter long coil is the direction in which the current is going to flow once you short circuit the coil. So let's say if I put the coil along y-axis like this, right? And some B is acting on it, magnetic flux. So now since the coil is, and let's say this coil is moving in the space, you know, with some velocity V. Now since this coil is parallel to y-axis, if you short circuit this coil, if voltage is induced in this coil, and if you short circuit this coil, let's say voltage is induced, E induced. Now voltage can be induced either in this direction, and if the voltage will be induced in this direction, the current naturally is going to flow from right and then go towards left. And if voltage is induced in the opposite direction, plus here and minus here, then definitely the current is going to flow in the opposite direction, right? So how do you know which direction you're going to take the current flow? It's very easy. Just choose a direction, irrespective in which direction the actually current is going to flow. Just choose one direction. So if I choose that it is going to flow in the positive y direction, that is positive j vector, I'm going to take the length vector. If length is 10 meter, let's say, I'm going to take the length vector is 10j, as simple as that. And then I'm going to put the velocity. Velocity is a vector. I'm going to put the flux density, which is a vector. I'm going to solve this equation. Remember, induced voltage is what? A scalar quantity, because you are performing the dot product operation right here, right? So the final operation is a dot product between the length vector and the vector which will be produced when you take the cross product of V cross B. So the final result is E induced, which is a scalar quantity. So let's say after calculating your induced voltage, the value turns out to be positive. If the value turns out to be positive, that means the direction of the length vector that you assumed was the correct direction. But if the value turns out to be negative, then your assumed direction of the length vector was incorrect. Current will flow in the opposite direction as you assumed, and the induced voltage is going to be in the opposite direction, and not in the direction in which you assumed because of the direction of the flow of current. So it's very simple. You don't have to think anything about which direction you have to choose. I mean, you're not going to know which direction the current is going to flow until you're going to solve the problem. So just take one direction, stick with it, and then solve the problem. Positive induced voltage, direction is correct. Negative induced voltage, your current direction, and the length vector that you assumed is incorrect. Just switch that. Your answer is still correct. The magnitude of induced voltage will still be valid magnitude. So go over this example, pretty straightforward example, and you will understand it.